This is a talk on quantum gravity, and I'm going to talk about what is usually the standard thing in quantum gravity to talk about, which is the problem of time, except I'm hoping that it's going to be a new set of questions about the problem of time. I'm going to be describing some approaches to quantum gravity that are recently being discussed, and I'm going to try to convince you that there have been great changes in what people are asking in quantum gravity in the last few years. So, all right, so then let me first start with the usual problem of time. This is the talk that my PhD supervisor could have been giving 20 years ago, I guess, or 15 years ago. So, quantum gravity as a quantization of general relativity. So one should start from general relativity, which is the theory that we have. So there's the Einstein equations, which describe the interplay between the geometry, between space-time, geometry described by a metric and curvature, and matter given by T mu nu. And the solutions to the Einstein equations are manifolds with a given metric. Now, there are two things to say about the Einstein equations, which I'm sure you all know, but let's set it up. One is that the metric is a dynamical field, not a background geometry. And the second is that the metric is not the correct physical quantity. To say what the correct physical quantity is, you have to take into account the symmetries of your dynamics, and the symmetries is invariant under diffeomorphisms of the manifold, maps of points in your manifold to other points. Now, being invariant under diffeomorphism means that the point is not physical. What is physical is an event. And an event is something that is marked, labeled by a physical interaction, such as the photon that comes out from the screen hits your retina, and that is an event in your causal past. The formal way of saying this is that the correct physical quantity is geometries, which is the metrics modeled out by the diffeomorphisms. That should be straight in there. That is, you can have several metrics describing the same set of events with the same order, right? So it's the events in their order that is the physical quantity. So geometries is what you want, in the sense that that is what is physical in general relativity. Now you can consider the following situation. Let's say that you have that your T mu nu is 0, so you have a universe with no matter. Then this idea, so a simple way to say what the problem of time is that since events have to be marked by actual physical things interacting, if you have nothing to mark your events, then you can basically map every point to every other point. Or to say it properly, time evolution, the 3+1 version of general relativity that Julian was describing earlier, in 3+1 GR, time evolution is a diffeomorphism. That is, it does nothing. So it is a constraint instead of a proper evolution. So if you try to make a quantum version of a constraint, you end up with the famous Wheeler-DeWitt equation, this here, where you have the quantum version of a generator of diffeomorphisms acting on the quantum version of geometry of the entire universe now. But it's not really a Schrödinger equation. You have a 0 on the right-hand side because the evolution is really a diffeomorphism. Now, this equation has been around for a long time, and it has been pretty impossible to make sense of it. There is a bunch of problems with it. One of them, for example, is the question of, is the wave function of the universe a physical quantity? Like, who could actually possibly see the wave function of the universe? You actually have to be outside, or maybe the very last person in the universe might get to see the whole thing. But otherwise, this is a strange idealization. But more relevantly, how do you define observables? So normally you define observables as using commutators with a Hamiltonian. When instead of a Hamiltonian, you have a Hamiltonian constraint, it's not clear how to do that. If you can't define observables, then it's not clear who is evolving in time. So in many ways, the problem of time is the problem of defining observables, or basically making sense of the right-hand side of this equation. And that has been a long-standing problem for a long time. So, and it still is so. So, for example, in loop quantum gravity, a lot of progress has been made on this equation. So there is explicit form of the wave function of the universe that exists. There is explicit form for the Hamilton constraint that's also out there. So they can write down the quantum version of this form in all detail, but it's difficult to check whether if you take the classical limit of this, you recover the Einstein equations. In order to do that, you have to basically address these questions here. So that's basically the standard version of what one should be doing in quantum gravity.
Excuse me, a question.
Yes?
So if you have a flat space-time and
Yes.
have a field graviton on top of it,
Yes.
whether this field graviton is an excitation or still the state with the graviton still be regarded as a ground state with such as a constraint.
Sorry, the state?
The state with a field graviton, say flat space-time with a field graviton, whether that would be regarded as a ground state satisfying this constraint, or this will be viewed as an excited state. The things that cannot define events using purely graviton. So treating graviton as a matter rather than.
Yeah, that's a very good point, actually. It doesn't show up in the way that you do this because you're not just restricted to perturbations on a flat space-time. This is supposed to work in a more general context. But in general, whether you could just do the whole job of describing events just using, I don't know, gravity waves or gravitons or something like that is an interesting thing, but it doesn't affect the fact how to make sense of that. Now, how does this, so what I want to tell you is that basically in the last 5-8 years or something like that, the questions have changed in the sense that the emphasis of what people are asking each other, what can your theory do, the emphasis of the questions has changed. And it's interesting because basically the new important challenges for quantum gravity, and that is my main statement really on this talk, actually come from observations. So traditionally quantum gravity has been something that you could never do any observations with, right? That the Planck scale is tiny, tiny, 10 to the minus 35 meters. Therefore, what you had to go on is mathematical consistency and conceptual clarity. But that is not true anymore. There is a long list of things that are presented as challenges to quantum gravity. So one set is the whole field of quantum gravity phenomenology. I'm not going to say very much about this because the prime instigator of that field, Giovanni Amelino Camelli, is just there. So you can ask him afterwards about what is the current hot things to look for. But this is actually an entire field. You can look up this workshop in that area that was run at PI a little while ago by Sabine, who is also there. So there is possible signatures of quantum gravity theories, at least at the phenomenological level out there. A very important class of those is possible constraints on Lorentz invariance violation. So, for example, if your quantum theory of gravity postulates any sort of microscopic structure of space-time, such as discreteness or non-commutativity of space-time, it's very likely that you violate Lorentz invariance. And there are pretty good constraints on how much you're allowed to do so. So certain kinds of violations at the Planck scale are already ruled out by observations. So all of these things are fairly basically astrophysical and other fairly direct observational checks on a quantum theory of gravity. Then there is there is observational cosmology. So the message really from observational cosmology is that we only know 5% of the universe. It could be that dark energy and dark matter can be explained by adding another field or some small modification of what we have, but it's also highly likely that you need new physics. And quantum gravity is supposed to be the field of new physics. So if you are a quantum gravity person worth your soul, you would actually be looking at these open questions and all of the unknowns in what is seen out there and try to see what you could explain. Not only that, but you might also have the ambition of understanding the inflation in a deeper way. So you could think of inflation as a phenomenological theory at the end of the day, a very successful one, so you have very few ingredients explaining a lot, but you would like to know what it is that underlines your scalar field and potential. And then there's LHC and there's so on. So there is a lot of challenges out there that if you have a quantum theory of gravity, you're actually pushed to say, can you say something about any of these things? In order to say anything about observations, of course, you have to sort out the business of observables. In particular, what you need to do is to have the low energy limit of your theory. To have the low energy, you actually need to have a fairly straightforward notion of time. To define energy, you don't just need time, you need time translation invariance. To be able to distinguish low energy from high energy, you have to have some notion of time at some level. So what's going on then is that given that you have all these new challenges, people are starting to consider more and more whether some notion of time is allowed. So roughly speaking, theories that have some notion of time can say something in that direction, and theories that do not have a more serious problem. And these questions of time are now being revised in interesting ways. So there are three kinds of questions I want to discuss. One is, well, is it just, do I need time, or I do not need time? It could be, how much time do I need? I need a little bit of time. And I will discuss this in the context of the approach of causal dynamical triangulations. And then whose time is the relevant time? And so that would be analog gravity that I want to say something about. And could you have, is time what goes in, is time the G naught naught of your G mu nu, or could you have a fundamental time even when you don't have a metric, or you don't have a geometry in any form? Okay, so the first one, causal dynamical triangulations. So that starts off conservatively enough, as you start off from what we had before, that we need a quantum version of a geometry. And the way that you proceed to make a quantum version of a geometry is first by regularizing geometry. And you can regularize geometry using triangulations. So if you have equilateral triangles and you stick them together, then if you have flat space, you would have 6 triangles around the point. Whereas if your space is curved, you would have either less or fewer depending on whether you have a positive or a negative curvature. So the deficit angle in the way that you stick triangles is a way to express curvature. So if you have now this form of geometry, regularized geometry, you can simply translate the Hilbert-Einstein action into an action in terms of triangulations, which is called the Regge action, by mapping the usual quantities to triangulations instead. Now, the interesting part about that is that, of course, there's a Lorentzian and a Euclidean version, which is, do you have an eye or no? It's a path integral. Now, at the end of the day, the important result is that Euclidean and causal are 2 distinct universality classes. So Euclidean ones are the first ones that people studied, because it's always easier to have a Euclidean sum. It's basically a statistical sum. And they were studied in the 90s, and they turned out to have bad behavior. So basically, Euclidean dynamical triangulation is the sum over all geometries. Do you have another one? Because I'm spending my whole time rubbing this.
Yeah. We have the red one, which looks like a pencil. It's good. There. Just press the clip.
Okay. All right. Okay. So the Euclidean dynamical triangulations, you basically perform this sum, and you find that there are 2 phases, and they're both bad. Either your geometries are just all triangles stuck on top of each other, so you have a crumpled situation, or you basically get these things that look 2-dimensional filaments, so they're also sick. So what dominates is always something sick. However, if you do keep track of the I here and you stay causal, you get something else. So what does it mean to keep the I in terms of triangulations? It basically means that time has always to move on. So in a continuum version, you're not allowed to split. You're not allowed to have spatial topology change, because at this point the lapse goes to 0. So in triangulated version, this would be the analog. In the causal version, does not allow any spatial topology change. So you always move from time t to time t1 to time t2, so you always go up. And that is basically having a time, as you can see there. Now when you have a time, you get all sorts of nice results. So you get smoothly varying geometries. So here the universe starts from nothing, and it gets bigger and bigger, then goes back to nothing. And the thing to note is that the size of space does not jump around a lot. It kind of smoothly varies. That's a very difficult thing to get. You get three-dimensionality emerge dynamically. So you can study the Hausdorff dimension of your world when you live inside the system. And you can also make a prediction for the high energy physics. You can study the spectral dimension if you are random walking inside such a triangulation. And you can find that it's four-dimensional at large scale, but two-dimensional at small scale. So there's a prediction that the world at Planck scale is two-dimensional. But now the interesting part is that essentially what you have is a statistical system for quantum gravity. And now you can ask a different question than you could in the standard canonical quantization, which is, okay, time is essential for your good behavior, but how much time do you need? Because now time is a particular type of triangulations that you allow in your sum. So for example, having less strict time means relaxing the causality condition, which means allowing more topology change in the system while staying in the same universality class. So this thing of having a system that describes a particular universality class allows you to weaken the conditions of time and ask whether you're still in that universality class. So here then, the lesson that I get from this particular approach is that it's interesting to ask how much time, not necessarily whether you can have time or not have time. But another question is which time? Again, this question of what does it mean to be Lorentzian and in a curved spacetime. And my example theory here will be analog gravity. So analog spacetimes are concrete models of emergent geometry. In the sense, emergent geometry means that the effective low energy theory is radically different from the high energy microphysics. So they started off by Bill Unruh as a sonic analog of black holes. So the original idea is that basically if you considered a fluid, say a waterfall, you could think of it as an analog of a black hole in the sense that if you're inside this fluid, then your sonic light cone, if you like, your sonic cone, would get distorted because of the speed of the actual fluid. And at some point, if the speed of the fluid is actually larger than the speed of sound, then you basically have a sound horizon. So the original idea of Unruh was to look at that as an experimental lab analog of black holes. And that is something that is going on, experimental analogs of black holes. But the interesting thing for us here is that while the fluid is clearly sitting in a room in the lab, so there's flat space, so fundamentally there is flat space, if you are an excitation inside the fluid, you don't see a flat space. There is a simple theorem behind all of these constructions that says that if you have a fairly generic fluid and you're a perturbation inside it, so you're inside the fluid, you would be seeing an effective metric, an acoustic metric, which would make you think that you live in a curved Lorentzian spacetime. So now what do you have? You have the fact that even if at the background you have a time, in fact, a flat spacetime, perturbations, that is internal observers inside the system, see a curved Lorentzian geometry. So it may be that getting something curved and Lorentzian is actually very much to do about being inside the system, not something that you have to build in your theory to start with. And a common way to think of that is to compare, you can think of that more broadly in terms of emergent spacetime, by comparing the fluid dynamics to the underlying molecular dynamics theory as the analogy between general relativity and the quantum theory of gravity that you're seeking. So, can I have 15 more minutes? All right, and you may now note that if in the fluid there are waves, while in the fundamental theory there are none. So could it be similarly that in general relativity, the relevant quantities, which is the geometry or the curvature, do not exist in any form in the underlying theory? So how much of what we see is just an effective thing that happens either because we are inside the system or because we are at low energy? So for analog spacetimes, we found that Lorentz symmetry is because we're inside the universe. But you can go further, and you can discuss condensed matter or quantum information approaches to quantum gravity. And you could ask, should there be any geometry at all in the fundamental theory? So not only could you possibly get the Lorentzian curved geometry by being inside the system from something that is flat from the outside, but you could also get it from something that is not even geometric. Okay, so this is the part that I don't have a great deal of time to talk about, but I'll give you the basic flavor. Could you have a fundamental time before you have geometry? And what could that do? So this would be a scenario where you say that there was the Big Bang and then there is us later, and we live in a world with geometry, but initially there was no geometry. And just geometry was born through a phase transition somewhere in the history of this. So how do you say that there was no geometry? I would presumably say that there is no notion of locality, and there is no symmetries like translations, rotations, and so on. That these are characteristics of being in the geometric phase. And you can make simple systems describing this. So you could model that by saying, so say that your world was made up of n systems, where n in this case is 8. So I have 8 things making up my world. I could say that the world is not geometric, so there's no notion of locality. Say when everybody is connected to everybody else, it's just a soup of stuff. While I have geometry when my system freezes at low energy to something much more regular, where I could identify symmetries like geometric symmetries of that. And I would also like the system to have matter at that level. And I can actually model such a transition. So there's a simple model that you can make that we played with, where you just put degrees of freedom on the connections of your graph that are basically 1 and 0. So 1 is when you're connected and 0 when you're not connected. So you have basically a quantum information system, if you like, of connectivity, which then, if you cook up an appropriate Hamiltonian, can condense into a system that that has symmetries that you can identify as geometric symmetries, plus matter. In such a system, you can also discuss things like the speed of light. So as your system becomes less and less connected and goes from the non-geometric to the geometric phase, you could also define a speed of light, which is how fast do signals go from one spot to another spot in this system. So going, say, from a point P to a point Q in a lattice, using local steps, takes a finite amount of time, which you can calculate simply by looking at the norm of commutators of operators between P and Q. And so that defines basically a speed of light in any sort of simple system like that. And you could see that what happens here is that the speed of light depends on the dimension of the system. You could look at the transition of the system in time as a dimensionality going from nearly infinite at the Big Bang to something very low here. And the speed of light falls with the dimensionality. So the speed of light you can calculate is proportional to the dimension. And you could then, once you have a speed of light, you can make all sorts of comparisons with existing phenomenologies, such as variable speed of light cosmology. So in particular, what's happening here is that you can have a very simple form of expansion of the light cones initially. So the usual horizon problem is said in the following way, that if this is the Big Bang and this is us now, then this is the forward light cone from the Big Bang, and that's a backward light cone from now. And there's a problem because there's no causal mechanism for these points to be in the same temperature. So what happens here is that initially you just have many more connections, and so that opens up the light cones, which is a way to understand the fact that the speed of light changes with the dimension. So the point of these systems is that you can start with something that just has zeros and ones and end up having a speed of light and end up having some notion of geometry at low energy. And at that point, you can move on to discussing the things that we saw before in the analog gravity approaches and so on. So a possible situation is that you start with no fundamental geometry or gravity. There is a fundamental time in your Hamiltonian, or there's a fundamental time somewhere in the background in your system that allows you to solve all the existing problems. And what you need to do is first consider emergent observers that are inside your system, and then discuss the geometry that they're going to see being in the system. So their geometry is going to be different than the fundamental one for two reasons. One is because they're inside the system, and the other is because they don't have access to the details of the system. So there is then the possibility that you have a fundamental time in the system, which is, however, distinct from the geometric time, that is the G0 component of your emergent metric. Now, if such a scenario could work, which is basically what's going on behind a number of these approaches, then you would basically say that you can escape the problem of time. It just looks like it's there because we don't have access to the macroscopic theory. So that's my end. What I want to say is basically three things. One is that, at least as far as I'm concerned, I don't think that many people would actually disagree right now. The questions that are being considered most important right now in quantum gravity research are actually driven by observations, by trying to make contact with what's out there. Difficult as this may be, I'm not saying it's easy, but I'm saying that the questions that are considered important are those that can connect to observations. The second is that the standard debate of is time real versus time does not exist might be neither here or there. Maybe neither of the two is correct. That in the old arguments, always this time referred to the geometric time, but there is the possibility that you have a fundamental time without the geometry. And finally, my own bet is that, well, geometry is not fundamental, so that is where all these problems came from. And here I have the references to everything I discussed. Thank you.
One observation is that when you consider the period of weak equation, H applied on the physical state equals 0, this is very similar to when you consider quantization of gauge theories in the temporal gauge, where we have the Gauss's law imposed on the physical state. However, this procedure gives you automatically non-normalizable state. So before you can say that there is a problem of time, you have to actually regularize to get out of this. You cannot just consider automatically this non-normalizable state. For example, you can get into very easily into contradictions. For example, you know that this operator has a non-zero commutator with all kinds of...
Yeah, but one does regularize. So in the proper version,
Yeah.
if you do either loop quantum gravity or causal dynamical triangulation, you do regularize, but you still have the problem.
Yeah, well, the regularization is also one thing to get out a little bit out of this strength or something like this. Actually, we have worked on an example of by means of regularization, you can get actually explicit cosmic time dependent in quantum cosmology.
So I have a question about triangulations. You mentioned that at the latest class scale you get this classical 3+1
Yes.
dimension. So how much of this is put already at the beginning, or what is the dimension of this pieces that you glue together? What would be if I take a 5-dimensional elementary?
So you start with 3-dimensional building blocks to get 3 dimensions. Well, yeah, 3 dimensions out. But that is not really as significant as you think. Because, for example, in the Euclidean case, you can start with 3-dimensional building blocks and you get infinite dimensions out, or 2 dimensions out. So it's not tied what dimension you put in with what you get out.
I've got a comment first to which I'd like your reaction, and then a question. Let's start with a comment. It seems to me, I'm just a little bit doubtful when Renata and her group refer to calling these things quantum geometries. They don't seem to me at all to be quantum geometries. They seem to be classical geometries that are contributing to a Feynman path integral. So I just quibble with them calling it a quantum geometry.
No, it is a quantum. So the sum is a quantum sum. It's a quantum path integral.
There are geometries that go into a quantum sum, is my understanding. But that's a classical history. That's a classical geometry that's going in. I mean, the Feynman path integral is a sum of classical histories to which you attach an amplitude.
What would you like to see?
And it seems to me that these things that she shows are actually all individually classical geometries.
Well, but you have a superposition of geometries, right? So that's the standard path integral that you want superposition of paths. I mean, they're not classical paths in the sense that you include things that are not smooth and so on, but you have a quantum superposition of geometries. That's quantum superposition of regularized classical geometries. That's the traditional definition of the path integral. So I think they're doing what they say.
So it's quantum geometry rather than quantum geometries.
I'm still processing that.
Can I have my question?
Yeah, please.
Yes, when you were doing the dumbbell page, the black hole one,
Yes.
you talked about having an emergent Lorentzian
Yes.
geometry. Is that just any space-time with a Lorentzian signature, or is it one that satisfies the Einstein equations?
Okay, yeah, that's very interesting. You don't get the Einstein equations in any
Because
natural
that
way.
would be exactly, you see what
Yes.
for me is so characteristic about
Yes.
general relativity is precisely those constraints.
Very
It's
good
the origin
point.
of constraints.
Yes.
So it seems to me to claim that your one is getting anything remotely like general relativity is a little bit strong.
Well,
at
that
this
is not the
stage.
claim. This claims that you can get that getting a Lorentzian geometry is not very difficult. You just have to go inside the system, and then you kind of get that. And that seems to be fairly generic. It also says that the Einstein equations are very difficult to get. So that's the basic statements of the whole approach here. So there is not. You don't get the. On the other hand, you also get other things. For example, you get Hawking radiation, which seems to then be independent of whether you have the Einstein equations. So that's also interesting.
Yeah, but
So when you write down this action, this path integral, do you just use the Einstein term, or you add the entire infinite number of curvature invariants that you could have added?
No, so the way that this is done is basically with the Einstein.
Or why?
Okay. So that's another interesting point, and that's so the two questions that are interesting to study in that is actually do you even need the Einstein weight? So you could say, why don't you add the extra corrections?
Well,
But in fact,
from an effective field theory point of view, you expect all of them.
right, but in fact, some of the work that they're doing is, does it even matter what you weight with? So it might actually not matter. So the way that it has been done is with just the standard Einstein equations. And I can give you a couple of references on trying to expand that, but it might actually not matter very much what the weight is, which is an interesting
I mean, how
thing
can it
itself.
not? There could be, what's an argument for why it wouldn't matter?
Well, I'm not saying that it wouldn't matter at all, that you could put any weight that you want, but you could be putting other weights that is not really the Einstein equations. That's basically the indications. We're not arguing that you can just redo the numerics with something else.
Right.
And that's what they're doing and get the same behavior. So if that's something that worries you or not is, I don't know.
I mean, in effective field theory, if you try to write down at some high scale, you would have to have, the higher curvatures are suppressed by your cutoff.
Yeah.
But if you're operating close to your cutoff, you need all of them. And gravity is not a normalizing the field. So you need an infinite number of terms in your action. So I don't
Okay,
understand
so
this
so I guess the answer is that these are not put in. Now, what would happen if you put them in? I don't know. I don't think
That
so.
would require background structure, wouldn't it? Here the whole approach is to not assume any background, whereas yours assuming some terms in an action, but there would be some background in which you can expand those actions.
No, I can write integral of r plus integral of r squared plus integral of r a b c d r.
Without some assuming any volume from anywhere or anything like that. I mean, you need to do an integration.
So don't you have an integration here?
I think triangulation, I don't know. What background you are assuming here in the triangulation approach?
There is no background.
Yeah, exactly.
No, but you have an Einstein-Hilbert action.
Mhm.
So what is that integrated over?
No, hold on. So you rewrite the Einstein-Hilbert action as a sum over all triangulations, all possible triangulations that satisfy the causality conditions, weighed by something which is just obtained in this way.
It's just the volume.
So it's just, yeah, it's missing an R somewhere.
Yeah, it's an advertisement, not a question. Since you mentioned the workshop of quantum gravity phenomenology, but I thought it might be interesting to some of you that we'll have a second installment of the workshop sometime next year, late spring, early summer in Stockholm.
Towards the city.
More questions?
Good. Well, then let's thank all of today's speakers.